about the cascode, there are some issues which some have brought to my notice. Inadvertently or advertently, I might have said wrong or right. I already said a 6-page problem about what's the bandwidth issue in cascode, which is now available on website, should be. Yesterday night I sent to TAs, they will put it on the website, and also maybe on Moodle, depends on them. So please look for issues about the, maybe there is an issue which I did not say correctly, or maybe I said it wrongly, either way. In any case, whenever gain increases, the bandwidth will go down, so there is no issue on that. What I was trying to only say, that if I have a cascode, then the change in bandwidth reduction per se from the simple to cascode will be not that large compared to the increase in the gains. Is that point final word is clear? That you may have enhanced gain and you will not have in the same ratio reduction in bandwidth. Is that clear? That is the all that cascode does. Okay. There is no issue in saying that cascode has the same bandwidth. If I said it per se, I do not think I have many times said bandwidth is not same, but in case I have said it, I stand corrected. Okay, so we start for cascode. So I have already given there, so you can read that. Maybe other class I will do today. Let me finish my, because I like to use something of today's class and tomorrow's, the Fridays, for the test. Okay, so 3 of the common amplifiers which all of us use in variety of applications is common source, common gate, common drain, or what essentially now popularly known as source followers. So today we shall like to do common source normal amplifier. We have already done day 1, we have been doing that often, so that I will not do it, but I will use one of the interesting common source amplifier, which is very interesting because it gives you a lot of understanding as well as it has a lot of features which we will just talk to you. There are 3 types of loads which we can use in the amplifiers. Of course, 4th one I have not written, in the sense that resistor is always possible. So I am talking of non-resistive loads, okay, that is active device which is acting like a load. So there are 3 kinds. One is called diode connected, the other is called current source loads, and finally one can have a linear load. Okay. Essentially we are trying to replace resistor by transistor in different modes of operations. Okay. That is the basic idea. Each kind of load has some advantages and some disadvantages. Okay. So we will see at least few of them if time permitting today, or at least on Friday. These are very relevant because we also will like to, at the end of this, all 3 all these amplifiers, why do you really need a difference amplifier at all if everything was so good with all of them? So why did we look for difference amplifier or diff amps? So I will at the end hit these all amplifiers some way, okay, and say that they are not good enough in many applications or most applications, and therefore we are looking for a differential amplifier. So I am not trying to say these amplifiers will never be used, I may show some applications, but generally why diff amps are used probably will be obvious if I limit them. Oh, this is does not give, this is not good enough. Oh, so look for something which all in all can I get little better in one, and that is the diff amp. So all these applications or all these amplifier I am talking because I want to show that they are also gain stages, but they have their own limitations and they must be overcome if you want a good amplifier, and that is the way we will come to it. So this is the pedagogy of this, why I am looking into this. Many of you have done this, so there is nothing new in that. I may rush sometimes, if someone does not follow, stop me. But otherwise there is nothing extraordinarily I am talking about which you have not done earlier. For example, one of the things which I may show at the end of this, which this particular part may not show, is the major worry was biasing in most of these amplifiers, which we normally never talk. Okay. So I will show you that why this biasing is an issue for us and why diff amp actually solves that problem. Okay. So the kind of things which I am trying to show in an integrated circuit, what are my problems if I use this, and what will be solution if I use diff amps. Okay. So that is why I am looking in such pedagogy fashion. Okay, so let us start with the first and the foremost amplifier. Common source normal amplifier I have discussed. This is an interesting amplifier which shows that there is a resistance in the source, and it is very popularly known as source degeneration. Okay. Now why this is relevant at times may be shown when the output appears for this amplifier. This is the kind of equivalent circuit which I draw from the Razavi's book. This is not mine, but this is what taken from Razavi's book method. I do not mean this specific, but Razavi's technique, and I like that technique simply because it explains from each node to each node what is happening in real circuit. Okay, that actually explains it very well, and because of that I thought Razavi's technique of putting an equivalent circuit is far superior than many other book in which people just say equivalent of this, put replace by this. I do not like that. This is a straightforward equivalent circuit of a MOS transistor along with other resistors and nothing great about. So here what I am doing is I have a load RD, which as I say will replace later with active loads, but right now keeping RD there. Then there is a series resistance RS to the source, and of course in this case also there are issues which maybe at the end I may show you. Normally for all simple solutions we say there is source resistance is 0. The input source cannot be without source resistance. So if there is a source resistance, it may create problem not at the low frequencies but at high frequencies. So right now since I am more worried about the gain, low frequency gains, I am not showing you RS values or some what is called R with the source itself, but otherwise that will also appear in circuits. Okay. Right now I am assuming that there are all effects of capacitance only come at very relatively larger frequency, and I am not looking into those frequencies. I am in a mid band low frequency area where gains are independent of frequencies. This is my assumption. We will see where it starts. So that is what our frequency response when we do for this, we will see that. So the way Razavi defines, you have an input voltage V in to the gate, between gate and the source there is a VGS, which is essentially he defines V1 as the voltage across gate to source, and from source to the ground there is a source resistance RS. At the output side, drain side, equivalent current source due to the input signal is GM V1 shunted by R0 and shunted by the body bias effect GMB times VBS. Finally there is a V0 output here, I should have said this is a V0 output across RD, and please remember source is not grounded, so RD should not come into parallel to R0 or any of the current source. This fact is clear, RD is not in across R0 or sources, it is to the ground. So essentially it is, if at all I should complete this circuit, okay, because that is what essentially the way I have shown. Is that clear? So please, that is the only difference from earlier work and this work. Okay. Now if I want to figure out the gain, I know gain is nothing but GM times the output resistance, and so we will figure out GM effective for this circuit, which is I out divided by V in, which is delta. If you are looking into delta kinds of the earlier analysis which we showed, there is another simple method I showed you, I is equal to GM V in plus GO V out. If you use that, then it is delta I out by delta V in is essentially same as GM. Now if this method what Razavi does, or I like to do, is we figure out GM effective for this circuit, we figure out R out for this circuit. You need not do all that also, but this also gives you a feature that how much GM is changing and what parameters GM is actually getting influenced by, because as a designer I want to know if I want to boost something what parameter is in my hand, okay, and that is something which this kind of analysis does, and that is why I say I like Razavi, not because of course he is a prolific writer, great analog circuit man. Okay, so first thing we do is we want to find GM effective, so we make V0 0, okay, and put V in, and find I out by V in, that is the standard technique to find GM. So I put V0 equal to 0, okay. Is that correct? I is equal to GM V in plus GO RO GO V out, GM is equal to I by V in, is that what we said it? So I make V0 0, so I ground this output, is that clear? As soon as I ground output, there is no current in the RD, so I just forget about RD. So I have GM1 V1, GMB VBS plus R0. So now I look at the relationship between input side V in, V1, and since this current I out, how much I out will be? Current through R0 plus current due to the body bias current source due to this plus current source appearing due to dependent GMV1, okay. These three currents must be summing to I out, okay. But the same current, since this is open circuited, the same current must flow through RS to go to the ground, there is no other path. Once the current comes through this, there is no way it can go there, so it has to go through this. So essentially drop output current is flowing through even the source resistance, which is true in a normal amplifier, anyway current goes through the drain to source, okay. So this is not very great. However, if you can see, since there is a RS here and there is a current here, there is a voltage drop here, okay, that we call Vx, okay. So we write what is Vx, the drop across RS, therefore it is Vx is equal to I out RS, is that okay? The drop across RS is Ix RS, which is nothing but my Vx. Signs are correct because current I have now chosen is downwards, so this assumption of plus minus is fair enough because I am putting current downwards, is that okay? So Vx, therefore it is not my, if I would have chosen this outer I out like this, then I would have put a minus sign on this right now. So you can choose either way, it is not, it is a matter of only your choice. I have put I out in, you may put I out out also, so it does not really matter very much, because if I out is outside, IRO RD finally which will come will be taken positive, but I out itself will come minus some way, so minus GM RD will come finally, okay. So it does not matter if I choose either direction of currents, the other things will take care, but this current sources must go from drain to source, there is no other direction for them, okay. So this is what it is, GMV1 into GMB VBS R0. So if I write this, this is the expression. If you see V in and if you see this loop starting from this ground to this ground, what is the way Razavi is telling, you go from this ground to this is a loop, isn't it? So drop plus this plus with signs whatever it is, this plus this must sum out to be 0 with proper signs, okay. In a mesh that net voltage is 0, okay. So we write then Vn is equal to V1 plus, because this is I use this plus minus so they add, so Vn is equal to V1 plus I out Rs, Vx is I out Rs, I out I substitute these values in I out Gm Vn minus, I am replacing V1 from here, okay. What is V1? Vn minus I out Rs is V1, Durvi, V1 is Vn minus I out Rs, I just substitute that Gm V1 is Gm into Vn minus I out Rs, that is Gm V1 plus GMB which is minus I out Rs, because VBS source to bulk and we are looking from bulk to source if bulk is grounded, so opposite polarity, is that okay? Source is at positive and this, but we want the opposite, so it is minus signs. So minus I out Rs is VSB. How much is the current through R0? 0 minus Vx divided by R0, and what is Vx? I out Rs, so 0 minus I out Rs by R0. This is Kirchhoff law and nothing very great going on, and this why I do this, as I say I like, of course since as I say I like all 3 books as much, all 4 books, but this method is very straightforward, there is no assumption, there is nothing we are missing. In terms, some terms are going to be smaller or large, this automatically numerically will reduce that term to small value. So you do not have to worry which term is stronger or which term is, but as a designer we will show you that this is not the ideal way every time, because then you solve everything. So from there we will try to deduce that if this means what, and then during design we will use our conceptual thinking for that. So first to get that, I think we should do analysis. So if I find out G effective from this, I get GMR0 Rs plus 1 plus Gm plus Gmb times Rs into R0. Just collect the terms and figure out Gm effective as I out by V in. I repeat, collect the terms of I out, collect the terms of V in, divide, and you get your Gm effective. So this is the expression, I got it. Now I start looking at these terms. If you say Rs is not very large, maybe a few kilo ohms, even then this term is of the order of 10 or 1 to 10, okay. Even if Rs is in kilo ohms, it is at least between 10 or something. This may be 1k is fine, but this into R0, that means this denominator is now getting 10 times R0 value equivalently. So if I just leave Rs, R0 cancels. I also say right now Gm is larger than Gmp, so I neglect that. So why I got it is actually Gm upon Gmrs, which is 1 upon Rs. Is that correct? Equivalently saying it is just 1 upon Rs. That means the value of Rs essentially is going to decide the gain. How much is my Rs value? Is that point clear? And this is very important for us, okay. Is that okay? So this is how you should look, having seen an expression which terms dominate, okay, and Gm is decided by what? Currents, but right now what I am getting is essentially Gm effective is not very much strong functions of Gm itself, it is only a function of the load I am going to put there, or source degeneration value which I am going to put there. This makes something interesting, because that means if Gm effective is not a function of technology parameters like thresholds or environmental parameters like temperatures, I am getting an Gm which is very very much constant, and to my value I fix Rs and I get my Gm. So that is designers thinking, oh, so I want to fix my Gm which is relatively constant, relative word has to be taught, we will see why, but otherwise we say relatively constant for most parameters of working. Then I say, oh, I got a good this Gm value which I can fix now, okay. So as a designer now I say, okay, this degeneration helped me to get something, a constant value for my choice. That is designer's output from this expression. As such, otherwise there is nothing great in this expression. So as a designer I started looking, oh, it is only Rs strong function, so Rs is my value which I must decide in my designs. Is that clear? So this is the learning part of that. The first part is just deriving, the second part is to learn, okay, what is that I got out of this expression, that is the design issue. So design issue says fix Gm by Rs, that is simple, okay. The second term in the gain function was R out, okay, and please remember R out is essentially the net output resistance, okay, but right now we first calculate the output resistance other than the load, because as seen from the drain side. So we calculate RO from here. What is the condition there to calculate output resistance? Put a voltage source at the output and short all independent sources, okay. The standard technique of circuit analysis, short all independent sources. Please, short means if the current source is there it should be open, voltage source it should be shorted. So do not try to show me some, sir I shorted something and it got funny, it may, okay. So okay, in my case I say okay, V in is 0. So from the same circuit I use the actual, I never change my circuit because I just want to say I do not want to go out of circuit from which I have started with, okay. So I grounded this. I still believe, since I am putting a V out here, okay, V out by I out is essentially what I will call as output resistance seen from the drain end for the transistor. So I say okay, what is V1 then? Since in this case this is grounded, okay, Vx, please take it, this is ground, this is ground. So what is the condition you are saying? V1 plus Vx is 0, V1 plus Vx is 0, or to say V1 is minus Vx, or to say V1 is minus I out Rs. Is that, this is opposite of this is grounded now, you bring this terminal ground, so it is minus I out Rs. Yes, V out is at the drain terminal. Whenever you calculate the output impedance or output resistance, short independent sources at the input or anywhere in fact, then actually apply a voltage source at the output which I am calling V out, which is entering a current I out, then the resistance seen there is V out by I out, or why should call resistance, if there are capacitance it will call impedance of that. Okay. Now RD is outside, see this is the output resistance seen into the device, the arrow you can see. Then I will shunt it, you see next line, the actual output resistance is RO parallel RD, okay, because why I do not want RD to be part of my calculations, because RD is an external parameter, it has nothing to do with device per se or circuit I am designing initially, that can be decided by the next system as well, okay. So I do not want to a priori decide what is RD, so whatever it will come I will put it anyway there, okay. So right now I say I am only calculating, is that should be clear now? So RO is seen in the device at the drain side, okay. Okay, so Vx is I out Rs, V1 is minus I out Rs, so I out again same, current this, then this is Vx which is Vx minus V out, you have to now remember the current is going from V out minus Vx divided by R0, what is the current in R0? V out minus Vx divided by R0, substitute all of this here, V out minus Vx by R0 is the current through R0 minus GMI out, all are minus I taken it because I can understand actually they are plus, all are same, okay. This current is sum of this plus this plus this, but the minus sign I am trying to say is because, can you tell me why? Because in real life the phase out will come, so I initially added that minus, but you need not put, you can put it plus here and still solve and there is nothing goes wrong about it, okay. So having done this I did all analysis and finally I get RO which is R0 plus 1 plus GM plus GMB times RS plus RS by R, collect terms of V0, V out and IO and divide and you get the output resistance R0 which is this, and the final R out as I say is this output resistance R0 shunted by RD. No, because that I out, see the problem what I removed is the, okay I will come back to it, but let me first finish this talking. This minus sign I did not put initially, okay, so I just took it, this minus sign which I am going to get, so I initially itself I used it so that finally I will get a minus sign, but then I kept using to make it that plus with an additional minus sign. The gain is GM minus GMR out and there I started plus GMR out, so I just thought I will make I out the other direction, so it will automatically phase out, okay. Just come to it, just wait, okay, I understood your point. Just let the major feature in this, R0 is quite large, why do I say so? Because again GM plus GMB RS is larger than 1 if RS is kilo ohms, maybe tenths. RS is normally much smaller than R0, so this term is negligible. So what this is larger than 1, so this is around 10 let us say, so 10 times the R0, so output resistance is much higher right now. So if you shunt it with the load and if the load is smaller than RO, then it is the RD itself, because whichever is smaller that will dominate. However, in some cases RD may be larger than RO, which will be this case? current source or cascode. For example, if I use a current source or a cascode at the load end, that will be even larger gain, larger than this gain, because there it is GM times RO times other RO. So that time the RD value equivalent will be even larger than GMRO, this GMRO, okay. There will be another additional RO coming in the cascode or in the current stage there, and therefore at that time instead of RD what will be the R out, whatever is the R0 RO you got, that will be your output resistance. So please take it, do not always use RD as a smaller or larger. RD could be larger if it is a current source which is replacing RD. If it is normal resistance, or RD can be smaller in transistors also. When if I use transistor as a resistance and I say RD is small, so which is the value, which way I can get? One of the active load I said, if the device is in linear mode or non-saturated mode, the resistance is very small, 10 less than 10k. So in that case RD will be always smaller. So the bias, how you did it, how do you put an active load on that, may decide RD smaller or larger than RO, and corresponding parallel combination one or the other may, in case they are equal you will have half of it, but otherwise one or the other will start dominating, okay. So typical value, if I write GM RO effective all that here, I get this expression. And now I again do the same thing, which terms is smaller, which term is larger, GM this is larger, this is smaller, this cancels. So I figure it out, roughly this becomes gain is equal to minus RD by RS. Now this ratio has very interesting features. What is the importance of a ratio? Any parameter which changes the resistance, like temperature, let us say it has a positive thermal coefficient, okay, TCR is plus positive, but since both are resistances and made out of same silicon, okay, their TCRs will be same. So if, of course in some sense you cannot say ratio will have same R plus dx is same, not necessarily same RS, because it is depend on the value itself also, but to some great extent we can say it will be always temperature independent. It is independent of all transistor parameters, nowhere W by L has appeared, nowhere beta dash appeared, mu Cox I am not even looking at it, okay. Is that okay to you? So in essentially now I have a gain of an amplifier which is controllable by me, independent of the device, okay. So this fact has to be remembered, that whenever you are looking for a good amplifier which is temperature independent or device parameter independent, you should use it. But what is the limitation I got out of this? Typically RD can be few kilo ohms, 120 kilo ohm, 30 kilo ohms, because larger I cannot put, that silicon it will eat. 10 will, this may be 1 to 5 kilo ohms. So what is the kind of gain I am looking for is 10, 20, 30, okay. So for all the advantages I got, I saw that my actual gains have come down heavily. So at the cost of leaving gains, I have now achieved constancy in gain. Is that okay? So if your requirement in a circuit is that at any cost I want gain should not change for anything, okay, whether it is sensor based device which is in some environment, audio systems where back noise is too high, you prefer that gain should be independent of all other inputs, okay. In that case this may help, but the idea is gain is smaller. So do not put this as a stage in which 1000 above gains are expected, it never gives that, okay. The first amplifier which we discussed was common source amplifier, and that is the word degeneration. Do you get the point why it is called degeneration? The gain has degenerated from its high value GMR this to a lower value now and make it as constant as possible, and therefore it is called source degeneration, okay. And that is one of the major stabilizing factor in any amplifier. Is that point clear? So any time I put a resistance in source, I am stabilizing something, okay. Now this issue we will use it in the feedback systems, where actually we will see, does this give you a feedback? It does. Okay. Essentially it is the first feature of a feedback. Okay. It is a series feedback, and we will see this stabilizes things. Okay. In stability criteria the poles will move away, okay, and then we say system is becoming more and more stable. This is the feature we want to now bring to you, that why RS in series, okay, of source. Is that clear? So these are, we have learned all this, but start looking from the design perspective. If I am given this, what should I choose? Okay. And that is how I am trying to explain. Okay, so second amplifier of my choice, common gate stage amplifier. Now this amplifier we already looked into some way. Where did we look into it? In cascode. The upper transistor was acting like a common gate. So let us do it as this. Now this is first time I am trying to show you, if I use other people's like Boyce or Paul Gray's book, they sometimes show a very different kinds of equivalent circuit. Okay, so I just thought I should copy from them. I am sure this is also one way of putting. The advantage of this circuit is it actually mimics the circuit drawn by you. Normally our equivalent circuit looks like horizontal, so we do not mimic the kind of circuit we have drawn. The way they feel it, and that is why I showed you that this circuit actually mimics the way you draw. Okay, is that okay? Point? Nothing great, it is only to show you that it looks like this. So here, why I am showing you this, because in layouts, when I do chip layouts for transistors and everything, I actually mimic this, and therefore if I have this, I have much easier to lay out. Okay, so I just showed you why such straight circuits are many times shown, simply because that is the way I will actually implement on chip, okay, during layouts. So just for the heck of it, nothing very great. Okay, here is this amplifier whose gate is grounded. Grounded, yes, just draw it, and of course as I say, I will go back to my standard Radavi's equivalent, because it is much easier to solve with that kind of thing, but I just thought I should show you, in some books the equivalent circuit could be shown in this fashion. This includes all capacitances. This I in RS is essentially like a V in RS, is that correct? Equivalent, it's if you convert it from Thevenin's to Norton or Norton to Thevenin's, I in parallel RS is equal to, equivalent in voltage is V in series to RS, some other RS, not same, series resistance. Okay. Gate is AC grounded, AC grounded. DC value you have to put for bias, okay, you have to keep it in saturation, but for AC I think I have made it clear that dot dot AC ground. Okay. So if I now put, if you are drawn, please do. Yeah, that is what I said, this is a current source. No, which is DC, there is no DC, so it is all AC. Oh, that is just to show bias. Okay, that is this. These are current, input current source. You have input V in series RS, I can Thevenin's convert to Norton and say it is I in parallel to, of course this RS and that RS is not same, okay, so slight, you may be right, okay, yes. So gate is grounded, so look for the lower, actually Radavi technique. I have gate grounded AC wise, there is a potential between gate and source which I call V1, there is a okay, so instead of this I have used, as because Radavi has used this, so I used a V in, please remember this RS and this RS are not same, current source output resistance is very high compared to the series resistance of the voltage source, which is comparatively very low, 100 ohm, 500 ohms, okay. So do not confuse the same RS, okay. So this is a current input through series resistor RS, this is V1, this is the output current GM1 V1, GMB VBS, R0 shunted RD, which is RD is bound to the ground, okay. Now I assume Ix the current at the output which flows through RD, is that okay? Your sign is taken care now, okay. But the same Ix can now in a circuit, it can go only like this, Is that okay, Surbhi? If current is moving like this, it should move up, okay. So that means this voltage IXRS is anyway negative, is that correct? So that sign which you were telling is taken care through the sign of Ix, okay. See earlier case, do you remember I used Ix entering, now I have used Ix coming out, okay. So if I use this equations, this, have you drawn the circuit equivalent? So let us do maths which is trivial. What is Ix actually? This is grounded, this is V0. So V0 by RD is Ix, okay. So the first equation is Ix is V0 by RD. Please check it sometimes, because you know I do not check it myself when I am writing, I just come here and show the slide. At times I may miss sign wrongfully, so please bring, as he said, we will also check again. Yeah, okay, essentially I am trying to say current source is still downwards. This is minus source to bulk, that is exactly is the value which I am looking for, but the VSB is always taken like this, source to, this is minus, this is VBS, so essentially its opposite direction, it goes down. Okay, you are, I am showing you as far as sign is concerned, I am correct on the sign, okay. So if I use the, please do not write before this, if I use this loop, input loop, ground V1 and this, then I say 0 is equal to Vin minus IXRS plus V1 is 0, is that okay? Just take a mesh from gate ground to the ground through the RS, okay. Vin minus IXRS plus V1 is 0, okay. Why I want to do this? Because from this I can write V1 plus Vin minus V0 by I, replace this Ix by R, this RS is 0. I also see V0, just a minute, I will come back. This voltage, please remember what I am looking for is the drop across this, which mesh I am looking, I am going from here to here, which loop I am looking, I am going like this, is that okay? Same common point na. So if I substitute this, if I use this Vin, drop across, let us say IR0 is the current in R0, so which is IR0 R0 minus V1 must be 0, because that loop is completed to the gate ground, is that clear? Drop across R0 is IR0 times R0 minus V1 must be V0, okay. Which means, and now what is IR0? IR0 is this current minus these two currents, because these three currents must sum up to Ix, is that correct? So this current must be this current minus this current. So if I do that, I substitute this here, I substitute this back here, and then figure out the relationship between V0 and Vn. Keep substituting, nothing very great. What is our aim? To get the gain, which is V0 by Vn. All that I have done it, I removed all Ix terms, all V1 terms, to get a relationship between Vx and Vn and Vo, okay. This is that expression, okay. At any given node the net current must be 0, is that clear, Raj? At any node net current, so whatever Kirchhoff law says, put signs accordingly, okay. So having done this all analysis, I get a expression of gain which is V0 by Vn, Gm plus Gmb into R0 plus 1, R0 plus Gm plus Gmb R0 Rs plus Rs plus Rd into Rd. Why this? This is what is Rd? That the output voltage Gm times Rd, okay. Now if this expression you see very carefully, this term Rs and Rds are smaller than R0, is that okay? Rs plus Rds are always smaller than R0, so I leave them. Gm times R0, this is anyway more than Gm Rs is more than 10, so 10 R0 maybe you add if you wish, but even that term I can neglect. I neglect one from here, so I cancel it here. It is Rd by Rs is all that I get. So even in common gate I haven't really achieved any gain. In fact it is very close to 1 only, as that common gate amplifier show, not voltage gain. Voltage gain can be ratio of Rd and Rs, but the current gain is how much? In common gate what is the current gain? Always unity. Source and drain currents are always equal, independent of what you do. Is that clear? So it is always unity gain for currents, but the output impedances and input impedances can be separate, so the gains can be different for different loads. Is that clear? Because currents are same, so input current drops will be different and output current drops will be different, and therefore the gains, voltage gains can be higher, but current gain always will be unity. Okay, that is the importance of this. However, as I say, this is not very frequently used so much as a good amplifier. What did I talk about common gate as an advantage? That it acts like a good current source. So what parameter I should figure out for this amplifier? Output resistance, because that is what I am right now looking for. So what is the method I should follow for output resistance evaluation? Short all input sources, independent sources. Put a output some in source of V out or Vx, entering current, let us say I out or Ix, Vx by Ix or V out by R out. It is the same method which we apply for anything, we should keep using the same techniques. Okay. Now if I do R0, what is the method I suggest? Short V in, but what is this case looks like? If I short only V in, this is like evaluating for a common source amplifier with degenerated Rs, okay, a degenerating source, okay. So I solve this again and I get same expressions which I did earlier, which is R0 into 1 plus GMB times Rs. This is the same analysis which we did earlier, it repeats here, okay. Now if I get this RO, what is R out again? This R0 shunted by Rd, okay. Just write down and then, is it larger or smaller? Anything multiplied by this factor to R0, the output resistance is higher. That is what cascade we were trying, no? The output resistance I want to boost. So the common gate, what did it do? Boosted the output resistance, okay. What is the requirement of a good current source? The source shunting resistance should be as high as possible, preferably infinite. What is the third parameter I should look into? Gain I have looked into, output resistance I look, which is the third one I should look for an amplifier? The input resistance. Do you believe it will be higher or lower? Lower, that is the fun part in that, okay. We will calculate. So what is it trying to do? A transform a circuit which has low output resistance to a higher output resistance, okay. So it is like a pseudo buffers, okay, that you are having a connecting at a lower input resistance this, but putting to the higher output for the next stage, okay, so that the next stage does not get loaded by this, okay. So this is interesting, but of course I repeat, if Rd is smaller, the output resistance will not be very high, okay. It may be a few kilo ohms, tens of kilo ohms, 20 ohm, 20 kilo ohm, 30 kilo ohms, okay. But Rd can be smaller also or larger than Ro also if I use current sources, okay. Is that okay expression, sir, everyone? Okay, so same expression, same statements. If R0 is greater than Rd, less than Rd, R out is either R0 or Rd. Now the next parameter of interest to me is the input impedance, okay. input impedance is seen from the input side, which is the, if Ix is the current here and Vx is the voltage, I actually calculate conductance Ix by Vx. Ix already I can find from here, Gm Vx Gmb Vx minus Vx by R0, okay, which is Gm plus Gmb by 1 upon R0. Since let us call this Gm dash, so if Gm dash R0 is greater than 1, one can see this value is larger than 1, this is by divided by R0, so Rin is effectively very low, okay. No, because no, Rs is external again, this has to be always understood. This is whenever we calculate any input or output resistances or impedances, it is seen in the device, okay. Output from the drain side, if it is a output at the drain, then seen from the drain side, input always seen from the gate or source side, okay. But the additional resistances will actually modify that value correspondingly. But if this is very low, even if Rs, it will further reduce it down, okay, so it does not really matter. So what is the advantage of common gate amplifier? That input impedance is very low. Impedance word is not clear because there are no capacitance as used, but I will come back to it. This is the issue where in frequency response, that capacitance when they come, which will have a dominant pole, may decide from whether R is lower or higher, okay, because 1 by RC. So this understanding that R is lower or more may help to even see, oh, this may be dominating kind of thing, is that clear? So observation based on what we have evaluated, okay. Is that okay? So I just now said the current gain in the case of this is always Ix by Ix, and therefore unity I0 by N. Now one interesting feature which I did not say, this was all under assumption of low frequency equivalent circuits. It will remain unity for a very large frequency, and our thinking was that even up to Ft it should remain 1, but in real life it does not remain 1 till Ft, okay. So maybe some other day or some other time, what frequencies actually it will not be 1, we will see that, but as of now you can say for almost all frequencies the current gain is almost, and this you must put in quotes, almost, and not necessarily all times, okay. So in a CG amplifier Rin is low but Rout is high, or to say we can convert a normal current source into a decent or great current source which is also voltage controllable, okay, because if you change Vin, the current value changes, so it is good VCCS. Now let us do the last amplifier among them, never is last but one you may say, okay. Is that okay, this part, anyone? But this is what you should, last part is important for us, okay. The last amplifier of my interest is common drain, okay, which is popularly known as source follower, okay. There is little difference between common emitter follower and source follower. Bipolar source followers are different in some sense to the MOS source followers, or sorry, common emitter followers in BJTs are not identical to common source followers of MOS transistor. How much they differ and why do they differ, leave it to you, okay. What is source follower word came from? It was found that if Vin and VGS of this transistor is such that Vin means V capital Vin, so that VGS plus input signal, if that exceeds threshold voltage the transistor is on, okay, and once that transistor is on the current is flowing across through the Rs, and drop across Rs is the output voltage, is that correct? The word source follower, so input current is proportional to input and that current flows through Rs, so output voltage is directly proportional to input, so source follows gate or inputs. However, one can say common drain because drain in this case is grounded, there is no RD there, okay. Since drain is grounded, So all voltage are referenced from the drain point, that is ground point. So therefore it is also called common drain. Okay. The drain is grounded means reference voltage has gone to the drain. Okay. So everything is measured from drain ground potential, therefore it was also named common drain amplifier. If you are looking for all capacitive mode equivalent circuit is shown here, gate to source CGS, gate to drain CGD, CDB plus external load is CL, GM VGS is, this is the VGS across CGS, so GM VGS is the current source, GMB VSB is the another current source, back bias if it is, R0 is the output resistance. Please remember RS is the load across which V0 has been picked up, okay, and drain is grounded. We will remove this capacitance next time. Before we start the differential amplifier, I will like to, maybe if time permit, no, not will permit today, I will see that whenever I have a series component in an amplifier which is connecting output to input, I can put into two parts, input side and output side, using Miller's theorem. When is Miller theorem valid? That is very important. You cannot use Miller theorem randomly. Okay. There are limitations or there are compulsions with which Miller theorem is valid, because that we will use again in the case of DFAM designs. So we will like to show you what is the limitations in Miller's theorem. Okay. Okay, is that equivalent circuit clear? So first thing what we will do is, as usual, remove all capacitances and solve for low frequency. I am going to do one or two frequency response for all these amplifiers one time, okay, and then the same procedure can be. And one of the technique which I taught this batch of in second year, which is zero time constant value or open circuit zero time constant systems, I will be able to show you which poles are dominant. Okay, so you do not have to evaluate all of them, you can figure it out which is the dominant pole which decides the bandwidth, because once I know the bandwidth I damn care much of the otherwise. Okay. So I must know my bandwidth, so which need not solve all of it all the time. So typical low frequency circuit is remove all capacitances, put an equivalent circuit V in input voltage at the gate, same gate to source voltage V1. This V1 word, as I say, I am using it from Razavi's book. If you want to put some other VGS value or something, it is fine, I have no objection. I repeat, I am saying this I have been using from Razavi's. I like this Razavi's technique, so I normally have been using his terms. This is my source, drain is grounded. Now in this case I assume that R0 is very high and I just forgot about it. Let us say, since this is my V0, the current in RS is V0 by RS. There is nothing else. If this is my V0, so V0 by RS is my current in RS. Since this is downwards, this voltage with reference to will become now minus V0, and then I substitute as usual all the terms. V0 by RS is the current which is GM V1, GMB VSB, substitute them again here and solve. Okay, you that writing symbols is yours. I think what I meant is the current source going down in series in parallel to GMB. I think I have made a mischief writing sometime VBS, sometime VSB. Please keep it as if the direction shown corresponding to that VSB. Okay. This VSB is minus VBS in real terms. So at times this sign probably gets into wrong mood. So please always assume whatever sign I am showing you, assuming correct signs, I am pushing the current down. Okay, so if I get first equation is V0 1 upon RS plus GMB is GMV1. My method like Razavi is look for input side, this is my input side, is that correct? This is V in, this is V1, this is V0, is that correct? This technique is very simple, यहाँ से यहाँ तक ground तक जाओ, voltage sum करो, so you get V in is equal to V0 plus V1, okay, or V1 is minus V0 plus V in, okay. Then this 2 V1 I substitute here, okay. I repeat, What is the method? First I actually look for these current sources going into this, then I look from this side, input side, I say V in must be equal to this. Is that clear? This is my V in, this must be equal to this. So that nothing very mischief done, only voltage here at the same node, same voltage must appear. So if I write that, I get this plus this is equal to this, Surabhi is okay. This is equal to this plus this, both ground. इस नोड के ऊपर ये दोनों sum must be this. Same equation I wrote. From there V1 is minus V0 plus Vn. Substitute V1 here. I get V0 1 upon Rs GMB minus GM V0 GM Vn. Collect the term for V0, collect the term for Vn, and I get V0 1 plus GM GMB Rs is equal to GM Rs Vn, or gain is V0 by Vn, which is GM Rs divided by 1 plus GM Rs plus GMB Rs. Two things you must remember: denominator is always larger than the numerator, marginally larger, because the other terms are smaller. Okay, so you can say the numerator is marginally smaller than the denominator. So the voltage gain of a source follower will be always less than 1. Okay. If there is no backgate bias, then you may say it's very close to the. So what is the importance of backgate bias? This is what I want to bring to you, why I have actually used this. Can you think? If there is no backgate bias, what is the gain will become then? Even close to 1, because GMRS by 1 plus GMRS is very close to 1. Okay. But as soon as I add the term GMBRS, I am actually increasing the denominator, but that means gain will further go down because of backgate bias. Is that point clear? So please remember why SPICE does not show your initial values, because if you are not using the backgate bias your analysis, it shows you are slightly away from your actual result. Okay. So this is why. Also an important fact you must remember, that the gain is positive, in the sense the output and input are in phase. Okay. Because in that loop current is in the same sense from input to output. Okay. And therefore it is always in phase outputs. Okay. And therefore it is always plus. If you look at the input impedance of such amplifiers, it is almost infinite, except if there is no capacitance, is open circuit. Okay. If there is a capacitance, it is decided by the capacitances. Okay. Typically input capacitance are very low, CGS plus CGB, these values are very low. So unless it is because 1 upon omega C, unless omega is very high, the input impedance will be always very high. Okay. At very high frequencies it may not be, because then 1 upon omega C may not be that high, and then it will start shunting, and that will be some kind of a pole it will start coming to. Okay. So I am not too much worried about input impedance. In the case of output impedance, what is the technique we use? Remove the Rs, remove Vin, okay, put Vx there, put Ix going through there, evaluate Vx by Ix. All input sources are grounded. Vin, wherever Vin was there, that I have grounded, because Rs is external. Impedance is always measured in the device. At the output I never took RD, so ये यहाँ Rs RD है ना. Okay, is that okay? Load is not my hand. Okay. Is that okay? That word was used there because in the source it was there, but essentially it is an output load. Okay, so if I solve this simple, this currents are same currents here, this, we can say, sign taken properly, then R0 is 1 upon Gm plus Gmb. What does this trying to say? R0 is higher or lower? 1 upon Gm plus Gmb. Gmb is same as Gm 1.6, so 1.6 Gm. Gm कितना होता है roughly? Millimoles, okay, millisiemens. So RO कितना होगा? few kilo ohms or lower, because if number is little more millimhos then it will be even lower. Okay. So the output resistance of a emitter follower is very low or lower, and input impedance is or input resistance is very high. So where do you think it can be used? In a buffer stage where input impedance you want to be infinite or very high, and you want to match the load which is a lower value, therefore output impedance should be matchable to that. Why it should be matchable? What is the purpose of match loads? Power transfer is maximum. Okay. So I want to put equivalent there so that I get maximum power transfers. Is that okay, I have drawn? This is very trivial, nothing very serious. Anyone who feels that I have done mischief something, please go into Razavi's book and correct your signs or otherwise. Though I have not copied from Razavi, but since I have taught Razavi for 10 years now, I almost know the way I must have done. Okay. So since I do not keep books anytime, so there may be a sign, in case you feel it, please look into Razavi's book. This is their technique, so it must be correctly there. Okay. Quickly I will show you and I will finish this. This is something which you now remember and note. Where do you want to use source followers? The first thing I just now said, if you need a system in which high input impedance and low output impedance, then you should use buffers, source followers as buffers. Now here is an issue, here is a designer problem. पहला part क्या था? Circuit issue था, circuit analysis कर दिया. What did we learn? We learned the problems now. Since VSB is related to V0, is that clear? VSB is related to V0, VSB also changes Vt. You know Vt is equal to Vt0 25 plus VSB to the power half minus 25. That means if V0 changes, Vt changes. If Vt changes, Gm changes. Okay. So Vt is now a function of output through this body bias. Now if Vt changes, the current will change. If current changes, or VOV may change, either way, okay, which means Gm may change. The worst may come if this series resistance Rs is even low. Think of it why I say, if not tomorrow I will tell Friday, if Rs is lower, the effects are even worse. So at least reasonable Rs hai to source followers may not be that bad, but if the Rs values are too small, then it will create this IDS variation or VOV variation very strongly, okay, and then all purpose of good buffer may not be actually seen. This is first issue which common source follow. The second problem which I see in buffers is, at the end of, please remember, input signal may be small, but normally what is the purpose of an amplifier? The output should be larger, that is why gain we call it, isn't it? The problem with this source followers are that their output and input swing both gets lowered. Now example, I give some values. Let us say I have an amplifier which I am using with VDD 1.2 volt, thresholds of 0.4 volt and over voltage of, these are not very accurate value but roughly okay. So we see the headroom now available to me is 0.4 plus 0.2 which is 0.6, which is almost half of the power supply. That means just to turn on device on, I have now so much voltage lost by me, is that clear? So I have very small swings now available for output or input, is that point clear? VGS minus VT to keep device on, below this you cannot turn on, above this, that means if this value is 0.6 or even more in some cases, then the available swing to you is very small, is that correct? So only when a very small signal amplifications you are doing, this may be fine, otherwise this may create a problem. So source follower should be always thought of very low signal amplifiers. Okay. However, low power low voltage applications, and you need many times in biomedical application larger swings for ECG for measurement, for example. Such amplifier may not be used because the swings are very small there. So accuracy of measurement becomes very small. So these are amplifiers which should not be used when you are looking for higher swings. Okay. So where do you use them? अरे कहीं नहीं use करना तो बताए क्यों? We use them. We use them as small swing applications are in the case of RF, for example, front end, which is low noise amplifiers, or in a normal other, not necessarily RF but other amplifier systems. The first stage amplifier, which is called pre-amplifier, you can have source. The reason behind, the input may not come from very high impedances, particularly if like in case of RF system, an antenna has 50 ohm or 75 balloons. Okay. Now you are inputting that signal, okay, which is at very low impedance. So the first amplifier which is going to amplify signal and the signal is very low, you are pushing it higher, at that time this may be good for you. Is that point clear to you? So do not think that these are not useful, but do not arbitrarily put any time source follower thinking उसमें क्या है, gain तो one and no great problems. Okay, it does create problems in actual designs. The last two applications will not explain, maybe I can, but you ask then only. The other application of a source follower is as a level shifter. What is level shifter? क्या होता है level राज in amplifier में? What is level? DC point. Okay. So the output Q point, that is DC value, is lower than input DC point. Why? VGS minus VT लगेगा ना आपको, so उतना नीचे VOV plus VT नीचे हो गया. I repeat what I am saying, if I want this amplifier to work, this value, ये VOV plus VT is VGS. तो यहाँ का वोल्टेज इस वोल्टेज से एटलीस्ट VOV plus VT नीचे है DC में. Is that clear? इतना वोल्टेज नीचे है. As a level shifter we can use this because the input level to output level can be brought. How much shift I can do? VOV plus VT, not very large, but at least it can go down. If you want further, you put another stage for that. Okay, you will reduce further. Then the last part, it can be used as a load. Okay, it can be used as a load if I have an amplifier. It's an N-channel device. This is my gate. This is my this. This is like a source follower, okay, and this can do a good job for you to give our RO high. You are looking for RO high, na? So this can give you good RO. Okay. These are some techniques. So this is why I brought this to your notice. When to use what is most important in designs. Okay. So source followers are only used for level shifting, for LNA, preamp, and for finally as load device. Okay. Do not use that as an amplifier of any other use. Okay. It has no good features. Okay. We are not talking about frequency response, which may have further impacts on them. When I go frequency response, I will explain more which one is even worse, okay, among them. Okay. Is that okay? Thank you for the day.